Good evening, ladies and gentlemen, and welcome to this centenary lecture under the auspices of the Royal Society of Western Australia. My name is Alex Bevan. I'm a member of the Royal Society of Western Australia, and I'll be your host tonight in the absence of our president, who is currently overseas and who sends his apologies. Firstly, if you haven't done so already, please could you switch off your mobile phones. Tonight we're very privileged to have Professor Peter Quinn, who is a world leader in radio astronomy, to be our centenary lecturer. Professor Quinn received a Bachelor of Science in Physics from the University of Wollongong in 1978 and his PhD in Astronomy from the Australian National University in 1982. Professor Quinn is an ICI highly cited researcher in astronomy and astrophysics with a special focus on computational cosmology and dark matter research. Following postdoctoral appointments at Caltech, NASA and ANU, he accepted a position as division head at the European Southern Observatory in Munich in 1995. He was awarded a West Australian Premier's Fellowship and took up a position at UWA in August 2006. In December 2008, he became the inaugural director of the International Centre for Radio Astronomy Research, ICRA, a new centre funded by the WA government, UWA and Curtin University. ICRA is focused on research excellence in astronomical science and technologies directed towards making fundamental contributions to the realisation and scientific success of the Square Kilometre Array. Professor Quinn became a WA Scientist of the Year in 2012, and he was made a Fellow of the Australian Academy of Technological Sciences and Engineering in 2013. And his address tonight is WA on the Threshold, New Understanding, New Discoveries and New Opportunities with the Square Kilometre Array. Please welcome Professor.
Sound, good. That's good enough. Good evening, everybody. It's a great pleasure to be here. We had a few technical excitement, I guess is the word, but our young friend at the back there fixed them, which is very good. It happens all the time, right? Big projects and small projects. I want to talk tonight about a very large project, something that's basically going to happen here in Western Australia and happen elsewhere in the world, which is really, I think, going to change our perspective on the universe. It's going to do something which I don't think anything has done in the history of science before, which is a big statement, but I want to try and back up tonight. So I talk about some of the understanding issues, some of the things we're trying to understand, some of the discoveries that we want to try to make, and some of the opportunities that this telescope called the Square Kilometre Array will bring to Western Australia. Let me talk about understanding, first of all, our understanding of the universe. This gentleman here, Isaac Newton, was probably the first person to give us an incredibly deep and meaningful view of the universe. He did that by making the universe predictable. Okay? So before Newton, the universe was a bit of a mystery. Things happened in the universe, the sun went up, the sun came down, the moon went around, there was eclipses, there were comets, there were all sorts of things happening, but nobody really understood why or how or what the rhyme or reason of those were. Newton invented this formula, okay, which is the universal formula of gravitation. It says that all the objects in the universe exert a force on each other called gravity, and that is proportional to the masses squared of the objects and the distance between them squared. So that very simple looking piece of mathematics is enough mathematics to be able to predict in great detail how the solar system works, how planets go around the sun, how the moon goes around the earth, when comets will arrive, when eclipses will occur. All the knowledge of those things is contained in that very simple equation. And so, Newton gave us predictability. The universe became a predictable and perhaps even understandable place to live. Newton's universe that he put forward in the 1800s had some other ideas as well. It had the idea that the universe was like a stage, like a platform, like the desert in Western Australia. It's infinitely flat and boring. It goes on in all directions, and nothing much changes in it. Okay, so the universe is like that. It's flat, it's a stage, and things just roll along if you push them in hard enough. The other thing that he said was that this force of gravity, which determines the way the universe evolves, is an instantaneous attraction. Everything in the universe, you and me in this room, and the moon and the sun and the earth, attract each other instantaneously. They feel each other's presence instantaneously. Signals travel across great distances, taking no time whatsoever to do so. So, universe of Newton, predictable, flat and infinite, and infinitely fast communications. Some of these ideas proved incredibly successful, as I said, in Newton's time, and they were carried forward into the next century. So in the 19th century, we had people like Rutherford and Maxwell, who took basically the ideas of Newton and used them to discuss other things, in particular atoms. So Rutherford, for example, had a picture of the way an atom worked, which was very much like the picture that Newton had of the solar system. There was something in the middle and things went around it on the outside. In the case of an atom, there's a nucleus in the middle of protons and neutrons, and electrons go around the outside on orbits, just like the Earth goes on an orbit around the sun. Same idea, different scale. And there was a force responsible for that, in this case not gravity, but electromagnetism. Maxwell said space is infinite and goes on in all directions, but he didn't quite say it was flat. He said sometimes it can have little ripples in it, waves, and these waves are responsible for basically moving energy from place to place in the universe. So again, two of the ideas of Newton were moved forward into this next century, 19th century. So is this all really true? Is it really true that the universe is predictable and infinite and smooth and, infinitely fast? Newton thought so, and when he looked at light, for example, he was one of the great inventions that he had was discover that light, in fact, has different colours in it. These are primary colours, and light couldn't be divided anymore. These were the primary colours. So he put a prism up to some light, and he saw this beautiful spectrum. Around the beginning of the previous century, in the early 1900s, people started to see a problem. Okay, when they looked at that spectrum in more detail, they saw this. They saw that the spectrum was, in fact, I pressed the button, covered with lots and lots and lots of black spots. Okay, so it wasn't smooth anymore. If you had a good enough instrument, a good enough prism, and you looked at the light, it started to have these little lines or black spots in it. So this was the real first sign that the universe wasn't actually smooth. If you looked at it very carefully, it got structure of some kind. Going a little bit further on in the early part of last century, around the beginning of last century, it was also shown that energy is not smooth. There's not waves like Maxwell thought on the surface, but energy actually comes in little packets, little bundles, little bullets, if you like, of energy called quanta. And that was an idea of this man, Max Planck. He basically said, I think energy is not smooth, energy comes in lumps. Just like the spectrum is not smooth, the spectrum has little lumps in it. And the reason why the spectrum has lumps in it is because there are some energies, there are some bundles of energy which are missing and some bundles of energy which are present. And so the universe is not made smoothly of a distribution of energy. It comes in little packets called quanta. And when you take this idea that energy comes in bundles, and apply it to the atom, you discover the atom has all these amazing sort of shapes that it can possibly have. And each one of those shapes corresponds to a different one of those black lines, if you like, on that spectrum I showed you. So that idea came about by appealing to the fact that the universe wasn't smooth, it was made of lumps. So, what have we discovered so far? We discovered that the idea that the universe is smooth was wrong. Okay, it comes in lumps. Okay, it's not infinitely smooth and flat in all directions. The other real surprising thing they also discovered at the beginning of the previous century was that the universe is not even predictable. Okay, so one of the great discoveries of Newton was the universe predictable. A guy called Heisenberg discovered the universe wasn't predictable. And the way he did this was to use the idea of Planck. So the Planck said, well, energy comes in bundles. Okay, so let's do a thought experiment. Suppose we want to, if the room is completely black, and I had a cricket ball and I threw it over there and it came back to me, okay? That would tell me that there's a wall over there, most likely. Right, there's a wall. Just bounced off, came back. So I did an experiment, threw out a cricket ball, came back, something over there, bounced off. What if the thing over there was a mosquito? Okay, throw the cricket ball at a mosquito, poor mosquito doesn't survive. Okay? So the ball was too big to do that experiment. I couldn't detect whether there was a mosquito over there because the mosquito was too small. The same applies kind of to nature. These little bundles of energy, quanta, photons are like cricket balls. And if I try to shine them onto something which is very small and delicate, like another atom, it perturbs it, it breaks it, it changes it. And so I cannot make an observation of an atom with infinite precision. The actual fact that I observe something, shine a light on it, sometimes changes the atom itself, because the atom is very delicate, okay, like the mosquito is very delicate. So in fact, if I shine photons onto an atom and they come back, I've actually changed that atom. And so the universe then becomes not predictable anymore. You can't say with infinite precision anymore where that thing was or how it was moving, because the very act of looking at it changed it. So we're starting to cross off some of the things that we thought were sacred, that the universe was predictable, it was smooth, and then along came Einstein. Again, beginning of the previous century. The beginning of the previous century was an amazing time. We had Planck, and we had Heisenberg, and we had Einstein, all within about 20 years of the beginnings of the last century, turned physics on its head, okay? Einstein came along and said, well, hang on a second, guys, space is not flat anymore, space is actually curved, and oh, by the way, there is a speed limit. Nothing can move in the universe faster than the speed of light. So all of the things that Newton hailed out, flat universe, smooth, light, predictable, no speed limits, all those things completely changed at the beginning of the last century. Complete revolution in our physical understanding. Based upon that physical changes to our physical understanding, we made some amazing advances. Humanity made amazing advances. Because we had the theory of Planck, because we had the theory of Einstein, we could do things like figure out how molecules work, figure out how to build a GPS satellite network, because you need to do not Newtonian gravity, but Einstein's gravity to figure out how GPS works. So GPS satellites and gene folding and the expanding universe and all the things that the amazing discoveries of mankind in the previous century, a lot of that depended upon this revolution in physics that happened in the early part of the last century due to Mr. Einstein, Mr. Heisenberg, and Mr. Planck. So, and we've measured, in fact, we've done experiments. Basically, if you look at the way some stars move around each other and you measure the way they lose energy, and the prediction of that is exactly, this is a prediction, and that solid line is the theory of Einstein. And so you can see a lot of the theories all of these theories are not just theories, they've been verified many, many times over by very detailed experiments. So we actually got some faith that these theories are pretty solid. Okay, so with those two theories, over the last century, over the previous century, we put together a picture of the universe, of how the universe was born, how the universe evolved, and how it should appear today. So this is a kind of a cartoon, if you like, of the way the universe began. Over here on the left-hand side is the Big Bang, the beginning of the universe, about 13.7 billion years ago, and time runs across this way. So by today, as we arrive 13.7 billion years after that point, you've got all the stars and galaxies we see around us in the sky. And so the universe has kind of evolved from a very smooth, hot, expanding cloud of gas to something that looks like it's full of galaxies and stars. The analogy here is like the steam that comes out of the kettle. When the steam comes out of the mouth of the kettle, it's very hot and it's expanding, and as it expands, it cools, and as it cools, the water drops begin to form in the steam. Same analogy is true with the universe. The universe is a very hot, expanding plasma at the time of the Big Bang. As it expands, it cools, and as it cools, little droplets of stuff begin to form somewhere around this point, about 1 billion years after the beginning of the universe, and then there's a cavalcade and avalanche of structure being formed in galaxies and stars and planets, and all the other things we see in the sky are actually formed. So this picture is something that's a consequence of Einstein's ideas of gravity and also Max Planck's ideas of the way atoms work. We would love to understand in detail how this picture started and got to the end. This is just a cartoon. We would like to observe it actually happening, of course, on the Earth. That's one of the great challenges of astronomy today. We'd like to start here and look further and further out into space. And astronomy is fantastic. As we look further out into space, we can look backwards in time, and I'll talk about that in a minute. Okay. Astronomers, science used to go on these big 100-year cycles. Okay, so remember we had the 18th century, we had Newton, and we had this predictable universe, and everybody was happy and glad, and everything was fine. All of a sudden, they noticed this little annoying fact that the spectrum wasn't smooth anymore, it had these lines in it, created a huge revolution. So in the 1900s, there was this revolution, or crisis that led to a revolution in thoughts and a whole new physics. pretty much 100 years later, we're at the same point. We now have a new crisis in our physical understanding of the universe we live in. And it's a really interesting crisis. So we have two incredibly successful theories. We have Einstein's theory of gravity, and we have Planck's theory of the atom. So what are you worried about? Well, everything should be fine. The problem is the following. If you look at this formula here, which is Newton's formula, but basically underpins also Einstein's theory, what would happen if that distance there was very small? Like if we wanted to understand the Big Bang. So the Big Bang was when the universe was pretty much squeezed into an infinitesimal point. So when that becomes zero, you've got a real problem here, because when you're trying to divide something by zero, it blows up. It becomes infinitely big. So all the forces, the prediction of this equation and Einstein's work is all the forces at the beginning of the universe would be infinite. And so if they're infinite forces, how can you possibly have an expanding universe? Similarly, if the universe was infinitely small and it got down to something of the order of the size of an atom, how could it possibly be smaller than an atom? Because we know the photons, these Planck photons are the smallest chunk of energy there is. So how can we possibly squeeze the universe down any further than that? So it turns out, if we try to apply the ideas of Planck and the ideas of Einstein to the very interesting place called the Big Bang, both theories fail, which is terrible, because you've got two successful ideas and you put them together and you get a bad idea. It's not a very nice situation to be in. So there's something missing. There's a real crisis, if you like, in trying to put together a picture, trying to put together the theory and the observations behind that cartoon you saw of the evolution of the universe. When we try to do it in reality, we try to do it with mathematics, it fails. So how are we going to do this? So that's, of course, when discovery comes along. So whenever you've got a crisis, you need to have some new ideas. If you discover some new insights into nature, something you've missed before. So that's what the next part of the talk is about, discovery. We're looking for something. We're looking for something missing in our ideas about the universe. We're looking for something we didn't find before. We haven't put it into our equations. We haven't put it into our theories. When you're looking for something new, of course, one of the first things you do is build a map. So these guys here, crashed into the western coast, and they didn't have very good maps, right? So building maps was an incredibly important part of discovery. It's been an important part of discovery for hundreds and hundreds and even thousands of years. So we maybe have to build some maps of the universe that are much better than the maps we have today. These kind of maps are interesting and they're beautiful, but they're not terribly useful. We can draw dragons and lions and elephants and bears, but that doesn't tell us very much about how the universe works. So we can build maps like this. This is a map of the entire sky. This is the Milky Way. The Milky Way that we're very fortunate to see here in Australia. So if we go out in the ground on a nice dark night and lie on your back and look up straight at the sky, you see the middle of the Milky Way galaxy. This is our galaxy. It's a big dinner plate, spiral galaxy. We're about 2/3 the way from the centre. And when you look back towards the centre, you see the beautiful plane of the Milky Way. All this milky stuff here is, of course, millions and millions and millions of stars, all the light blended together. And this black stuff is actually dust and gas inside the Milky Way galaxy, which actually is the birthplace of lots and lots of stars. It's really interesting. The first people to really see this, of course, were the Aboriginal people. So the Aboriginal people were probably the world's first astronomers, 40,000, 50,000 years ago. And they saw the sky and they saw this, and they did something totally different. They didn't do this. This is the Chinese and the Greeks and the Mayans and the Aztecs drew lions and tigers and bears by connecting up, all the stars. The Aboriginal people were connected up not the stars, but this black stuff. Okay? And they made some really interesting patterns. One of the patterns they made is a thing called the Big Emu. Now, I had never heard of this until I came back to Australia a few years ago. I thought people were pulling my leg, that there was a big emu in this picture. But in fact, there is a big emu in this picture. There it is. Okay? So, the Aboriginal people knew this 40,000 years ago, that the galaxy had a big emu in it. But they had a totally different approach to doing astronomy, which is really a side story, but an interesting story. So we can build maps like this of the sky, but they're good maps, but they're maps from the last century, to be honest with you. We can do probably much better than that. So building a map, building a really good map is excellent, but once you build a map, you have to do things too. You have to actually measure things in the map. And so one of the things astronomers love to do is measure distances. And it's a very hard thing to do. Astronomers have to be really clever, right? I'm not saying I'm really clever. I think astronomers have to be clever because if you're trying to measure the distance to a light bulb, you can imagine you've got a light bulb out there in the car park, and with no other equipment other than your eyeball, can you tell me how far the light bulb is away? So you can't get on the other side of it, you can't go up to it and shake it. You've got to be clever and figure out some way of figuring out how far that light bulb is away. So astronomers use these kind of tricks, techniques to measure how distances are. So for example, if you have something, we call it a standard candle. If you have a star which has a unique brightness, okay, a particular star has a particular one star's worth of brightness. Clearly, if you see that star fainter and fainter and fainter, it's the same type of star, the further it is away, the fainter it gets. So by measuring, if you know the star that you're looking for, you trust that it has the same brightness everywhere in the universe, then of course if it's faint, it's further away than if it's bright. Called standard candles. Standard ruler is the other thing, okay? So if you measure a ruler up close to you and you put the ruler at the back of the room, the ruler's going to look smaller. So if you've got something else that you believe is a standard size, maybe the size of Jupiter or something, and you see Jupiter at different distances, you measure how big it is on the sky, the smaller it is, the further it is away. So there's some really simple techniques for measuring distance, and astronomers use these kind of things all the time. They also use something called redshift, and this is a really interesting technique that has to do with the light. So this is a picture of a pond, of a little pond, and what I'm doing in the pond is just dipping my finger in the pond and making waves. Okay? So the waves spreading out from my finger, and my finger's sitting still. So what would happen if I actually made my finger move on that pond surface as I dipped it in and out? So what happens then is something really interesting. As I'm dipping my finger in and moving it forward, the waves in front of my finger get compressed, they get squashed together, and the waves behind my finger get spread out. So this is the famous Doppler effect. And you all know the examples of this. You've probably done it in school, where the ambulance comes screaming by, and all of a sudden as it goes screaming by, the tone of its siren drops. That's the Doppler effect. In front of the ambulance here, you've got a high pitch, and below the ambulance, you've got a low pitch. The same is true not only with sound, but also with light. So if I have a galaxy, this galaxy, picture of galaxies, is another picture of the same galaxy. This is a picture of its radio waves coming off it. And these radio waves come off at a given frequency. And this is one particular frequency. It's about the same sort of frequency as your mobile phone. If that galaxy starts moving away from me, that will stretch that particular frequency out, make it longer. So if I stretch it out by, say, a factor of 10, make it 10 times longer, I know that galaxy is moving away from me very fast, and the faster it would be moving away, the longer this stretching out would be. So if I can measure waves, the light or the radio waves that come in from galaxies, and measure how much it's stretched, I can tell you how fast that galaxy is moving away from me. So knowing how fast it's moving away is one thing. How does that relate to how far away it is? And so this man here, Mr. Hubble, was the guy who gave us that piece of the puzzle. So Hubble is an American astronomer who did his work in the early part of the last century as well. And he discovered two amazing things. He discovered that the universe was really big. That sounds crazy, but he did discover the universe was really big. Before Hubble's time, people thought the entire universe was pretty much the Milky Way galaxy. There was nothing much outside. He showed that there were galaxies just like the Milky Way, much, much further away. So he discovered the universe was really big. The other thing he discovered was all these galaxies that he found were, as in the further and further away they got, the faster and faster they appeared to be moving away. So that's really interesting. They're all moving away from us for some, they know something we don't know, but they're all moving away from us. And the further they are away, the faster they're moving. This was the expanding universe. So he discovered also the universe was A, big, and B, expanding. So, and so now we've got exactly what we need. With the Doppler effect, I can tell you how fast a galaxy is moving away from me. And then Mr. Hubble's equation here, or his law, tells me how far it is away. So with the combination of Hubble's law and the Doppler effect, I can tell you exactly how far away galaxies are. So doing that, we've actually mapped the structure of the universe. We've actually done really well. So this is a picture, this is a little movie of galaxies that we know about. So this is real, it's not cartoons, these are real galaxies. And we started at our home Milky Way galaxy. We're moving out from the Milky Way out of the universe. Okay. So you can see the universe is full of galaxies, lots and lots and lots of galaxies. And not only is it full of galaxies, but these galaxies are not actually spread out at random. They've actually got some interesting patterns, the way they're actually distributed on the sky. That therein lies an interesting story in itself. But as you move further and further away from the Milky Way, you see these galaxies, and there's this beautiful kind of filigree, lacy, spider webby kind of pattern that describes the way the universe looks. Okay, so the universe isn't just smooth and uniform, but it's got this beautiful sort of structure in it, which are produced, presumably, when the universe was formed. So maybe one of the things we're missing in our understanding is what caused all this kind of, it's not like you just took a whole bunch of galaxies and just threw them on the ground. You get this beautiful pattern here. Where did that pattern come from? Maybe that's telling us something about the way the universe started. One of the other ways of measuring distances, which is more modern, is one of these standard candle ones. It has to do with this thing called a supernova. So this is an exploding star. This is the remnants of a star that's exploded. And one of the things we know about this is when stars explode, the maximum brightness that they achieve when they explode is roughly constant, independent of the star itself. Okay? So I can use exploding stars as a standard candle, and so I can use them to measure. If I can find an exploding star in a galaxy, I can tell you how far away that galaxy is. So we have a little satellite galaxy near to us called the Magellanic Clouds. It's a little neighbour galaxy of ours. And in 1987, it looked like that, and one day later, it looked like that. So this thing appeared out of nowhere. It's called a supernova. It's an exploding star, 1987A. And so these things can happen nearby to us. They can happen very, very far away in the universe. So we can use those again to measure distances. Therein lies an interesting story. So these gentlemen here were doing exactly that. They were looking for supernovae in nearby galaxies to measure the distances to those galaxies to make better maps of the universe. When they did this, they thought that they would just kind of reproduce Mr. Hubble's law, because they basically knew how fast the velocity of the galaxy was, and they knew how far away it was. Independently, they knew how far away it was, because they had the supernova technique. When they did this, they found that, Mr. Hubble had a nice straight line in his diagram. When these guys did it, they found that the line wasn't straight anymore. It actually had a curve in it, actually had this sort of funny bend in it. Okay? It bends up. So Hubble's was just straight. This one started to bend up. What that means is something rather profound. It means that the universe in which we live is not expanding uniformly like Mr. Hubble had it in mind. The universe, for some bizarre reason, is actually speeding up. As time goes by, the universe is speeding up. Now that is totally bizarre. Okay? Why is it totally bizarre? Well, you can imagine the universe sort of just coasting along and just, doing its thing and doing much. Or you can imagine the universe sort of slowing down, because when you throw something in the air, it comes down, it goes up to the top of its flight, slows down, stops, and falls back again. So you can imagine the universe kind of doing the same thing. But having something speed up as a function of time, the only way that can happen is if something's pushing. Something has to be pushing it. Energy has to be added to the system to make the universe speed up. So what the hell is this? What's this energy? Where is it coming from? What's pushing? We can't see anything pushing. Why is the universe going? So these guys won the Nobel Prize for that discovery in 2012. This is Brian Schmidt at the Australian National University in Canberra, and he's probably spoken to some of the people in the audience. He speaks all around the country very, very often. But this was an amazing Nobel Prize winning discovery. Again, by building maps of the universe, we discovered something we didn't know before. Remember I said we discovered this funny filamentary structure. We've discovered now the universe is expanding in a totally bizarre manner. So all of a sudden we're finding things which are things we didn't know before. New things that came from building maps of the universe. This stuff which is pushing, people have given it a name, it's called dark energy. Really bizarre title, but it's called dark energy. Somebody once described it to me like as if the universe was full of invisible bed springs. Okay? So you can imagine you've got a piece of universe here, and you push it, and it has a box, nothing in the box whatsoever. You push on the box and it springs back. Right? So that would cause you some consternation. But it's like there's an invisible bed spring. So the universe is full of this bound up energy like springs, and it's pushing the universe in all directions. So we would love to be able to understand this dark stuff which is doing the pushing, because I bet you, and lots of other people would bet you their house, that if we understood this, we'd understand why it is that Mr. Einstein and Mr. Planck theory doesn't work properly. We are missing here, effectively, not missing a small bit, but 74% of the entire energy of the universe has to be in this dark stuff, right? So it's not a little problem here, it's a very, very, very big problem we're talking about. So a lot of the energy in the universe is in this funny stuff that we don't really know what it is. It's probably telling us something really fundamental about physics and about the universe we live in. Okay, so we're doing really well. We're building maps, and we're getting more insights into the universe. But the maps that were built then, the supernova maps, they came from about, this is this cartoon again, here's the Big Bang, here's today, this is distance away from us, or this is time going forward. those supernova measurements were about here, okay? They weren't terribly far into the universe. We would like to understand all this stuff here, about 10 times further away than we can currently see, because about 10 times further away is when we think the very first little things begin to condense out of the Big Bang expansion. So we'd like to build maps, sure, we'd like to build maps that go down here, not up to here, right? So that'll tell us even more about this mysterious missing ingredients of the universe. So we have telescopes, we have the Parkes telescope, the famous dish. It's a big eyeball, collects radio waves. It does a really good job of seeing things over here. We have bigger telescopes, like this one, called the Very Large Array, VLA, in America. It's about 20 or 30 of these guys, and it's about 10,000 square meters. So because it's got more collecting power, it sees more stuff. If we want to get 10 times further away, we've got a problem, because if it's 10 times further away, it's not 10 times fainter, it's 100 times fainter, because it goes like the square of the distance. So we have to build a telescope, which is basically 100 times bigger than this guy, to be able to see back to more or less this place in the history of the universe. That's 100 times 10,000, which is 1 million. So if you had 1 million square meters of eyeball, maybe you would have a fighting chance of seeing back and building maps and doing all sorts of interesting observations back at this time in the universe. Okay, 1 million square meters, that's a pretty big telescope. How big a telescope is it? And this is where the transformational thing comes in. So this little plot here is a plot of pretty much all the major telescopes, optical and radio, that have ever been built, and how good they were. So over here on the left-hand side, you've got Galileo's little telescope, and it was about 25 times better than just using his eye without any telescope whatsoever. Over time, people have been building telescopes, and there were some really big, in the early parts of the 1700s, 1800s, there were some really big advances in telescope building. But ever since then, every time we've built a telescope for the last few hundred years, it's been 5 or 10 times. This is how much better it is in some sense than its precursor. So every time we've built one, it's been 5 or 10 times better than its precursor. That's pretty good. If you built a car today that was 5 times better than the car you built last year, you'd be very happy, right? So we've been doing pretty well at building telescopes. How big a step is building a square kilometre or 1 million square metres of stuff? The answer is, it's up there. It's about almost 10,000 times better than anything we have today. So it's a huge, I mean, in the history of telescope building, this is kind of unprecedented, okay? So if we're going to do this 1 million square metre thingy, we basically going to have to break all the rules. We're going to have to jump generations, figure out how to do something that's never been done before. So, what does 1 million square metres of telescope look like? Okay. So this is what 1 million square metres of telescope will probably look like. It's not just one dish, or 10 dishes, or 20 dishes, but it's thousands of dishes. Thousands and thousands of dishes, spread out over hundreds of kilometres. Okay. So it is a very, very large machine for doing science. It's unprecedented in some sense. It would be the world's largest scientific machine, the world's largest scientific facility. Okay? So the square kilometre array, which is 1 million square metres of eyeball, is exactly this. It's a transformational machine for doing science. And it would be truly impressive to see it built. Okay. So that dream is something that astronomy has been following for the last 20 years. Whenever you be so bold as to build something with 1 million square metres, you create all sorts of opportunities. Of course, the opportunity to see the beginning of the universe, to see the very first things that shone in the universe. That's what we're in fact building it for, to give us the insights to figure out what's wrong with our physics. There are other opportunities that building a machine of that size would also bring. So, this machine is going to be built. The square kilometre array is going to be built. It's going to be built in 2 places. Part of it, half of it roughly, in South Africa, and half of it here in Western Australia. And in 2012, we decided that was going to be the case. There was a bit of a bun fight before that, I must admit, between South Africa and Australia, and I think at the end of the day we all agreed to be friends and divide up this telescope into different parts. And I want to demonstrate that's actually a good thing. So we're talking about one observatory, the square kilometre array, 2 different sites, and probably at least 3 different technologies are involved in this telescope. So map building, of course, the big thing is build these really great maps of the universe. So you want to map the sky, and you also, once you build these maps, you want to look in detail at all the really interesting objects you find. So those are the 2 big missions, if you like, of the SKA. build maps and then look at detail of things that you've actually found. If you're an explorer and you find a hill or a bay, you may explore it in more detail. So, map building, the SKA will probably use 3 different kinds of technologies to do that. And I'm going to go through those sometime. At the low frequency end of the radio spectrum, that's about 100 megahertz. That's about the same frequency as your FM radio station, 96.5 FM, right? So, 100 megahertz is about the same frequency as an FM radio station. If we look at that signal range in the sky, we're going to actually see right back to the early universe. That's a very long wavelength. Very long wavelength means very far away. So we're looking very far back into the history of the universe. So when you listen to your FM in the morning at breakfast, some of the signals are very close coming from the edge of the universe, which is kind of interesting. So it looks at this first line. There's a middle frequency of around about the same frequency, about 1,000 megahertz, about the same frequency as a mobile phone, and that's a frequency, different kinds of dishes to be used for that, and that's a good frequency of actually looking very nearby to us, looking and mapping our own local galaxy. And then 10,000, 10 times bigger, about 10 times the frequency of a mobile phone. That's actually the frequency we use to look in great detail at some of these amazing objects. So we are starting to build. We are starting to build facilities here in Australia and also in South Africa. In Australia, the site is in the Murchison Shire of Western Australia, about 300 kilometres northeast of Geraldton. Murchison Shire is about the same size as the Netherlands, but it has a population of 120. No towns, 3 dogs, 2 cats, a few gators, whatever. It's a great place to visit. And it's great for astronomy because there is nobody there, right? There's nobody with their mobile phones, there's nobody with their microwave ovens, there's nobody with their electric fences and all that sort of good stuff, all of which generate radio noise. So this is a very radio quiet, it's like the equivalent of clouds in the optical. There are no radio clouds in this part of the world. So we're starting to build some of these things, and since about the middle of 2012, there's been a number of dishes. This is the 36 dishes which are out there. It's about 1% the size of the SKA. You can see the dishes out here on the horizon. That's just the tip of the iceberg in some sense. These are very special dishes. They have on the top of them the receivers, which are like a digital camera in the radio. So just like you've got a digital camera in your phone, this is a digital camera that works in the radio part of the spectrum. It's been developed in Australian technology. The other one is these guys here, which look a little bit like spiders. There's hundreds and hundreds and hundreds of these little guys out there. They don't move, they just sit still and they look at the very low frequency part of the spectrum. So what's going to get built in Australia and South Africa? In Australia, we're going to build in the next few years these spider kind of things and these dish kind of things. We're probably going to build about 100 of these guys and probably about 100,000 of those guys. In South Africa, they're building the dishes, probably about 200 of these dishes at the high frequency end. So the high frequency detail observation work in South Africa, the low frequency mapping work in Australia. So this mapping and deep investigation goes hand in hand across the Indian Ocean. And as we go forward into the future, we're building more and more and more. So the SKA is going to get built in steps. There's a lot been happening in Western Australia in the last few years. In particular, we built a new International Centre for Radio Astronomy Research. It's here in Western Australia. It's a joint venture of the University of Western Australia and Curtin University. We've got about 120 people, about 40 staff. We were ranked just recently as one of the top 5 radio astronomy centres in the world. So we've come a long way in the first 5 years, and we've been renewed with funding from the state government and the 2 universities to continue our mission. So we've got this new, vibrant community of students and astronomers here in Western Australia that didn't exist 5 years ago. We're also working with industry. So industry, of course, is going to be intimately involved in the SKA. This is where opportunities for industry come from. So they're going to help us build. We're not talking about building a few antennas. We're talking about building hundreds and thousands, or even millions of antennae over time. And so industry, we need industrial processes, industrial smarts, if you like, to help us do that. So ICRA has been building up relationship with industries over the last 5 years to help us do this. We have something here in town called the Pawsey Centre, which is a new supercomputer centre. It's $80 million of federal funding, which is here in Western Australia. And it's one of the top 20 supercomputer centres in the world. And that's going to be very much associated with taking the data from the telescopes and turning it into scientific information. I might actually show you now something slightly new. So this is a simulation that we did a few years ago of the universe. Now what we've done here is we're trying to understand how this sort of really interesting spidery pattern that you saw came about, and we can put into these big computers Einstein's theory, a bit of Newton theory, a bit of Planck theory, mix it all together, and hopefully come up with a simulation of the way the universe evolves and try to figure out some of these processes like dark matter and dark energy. So just recently at ICRA, we've been actually working on some of these new simulations to figure out if we can see some of this really beautiful filamentary structure evolving using new physics, using the physics of the dark energy. I'm going to show you what some of these supercomputer simulations can do. This is what we've done, as I said, was we put Einstein's theory, we put Newton's theory, we put Planck's theory together, and also added in some of this dark energy just for good measure and dark matter to see whether that makes a difference. Some lights down. So this is the early universe. This is the universe just after the Big Bang. As the universe is expanding, lo and behold, some of this stuff starts to appear. So this is actually some of this beautiful spider web kind of structure, which naturally evolves in a universe if you add in this dark stuff. Okay, so this dark stuff does a bit of pushing and rearranging, and it produces something which is very much like the real universe that we see around us. Okay, so we've got really, this is another way in some sense of supporting the idea that the universe is dominated in some sense by this dark force, dark energy, dark matter that produces this beautiful sort of imagery. So this is a supercomputer simulation. It's a simulation you're actually now flying through the early universe. You're flying through the universe as it's starting to form structure, as this condensation process is actually going on. And this sort of stuff is possible with a very, very, very large supercomputer. You can actually evolve with mathematics, all sorts of interesting physics, the actual evolution of galaxies. So these are galaxy-sized objects. These things here are galaxies, okay, and small galaxies and large galaxies. And this beautiful sort of spider-webby sort of filamentary structure that goes through the entire universe. So we're making progress. We're making progress with our supercomputers. We're making progress on the idea that the universe is dominated by these things. We now need to get on with the business of building the machine to actually tell us what the hell this stuff is. So the supercomputer simulations, as I said, are something that basically is one way of us figuring this out. We are now about to go forward and start constructing the SKA proper. The things that you saw just recently, just before, are little what we call precursors or pathfinders. They're about 1% the size of the SKA. The true SKA will be, of course, 100 times bigger, right? And 100 times more challenging, I'm sure. So, just to give you some idea of what's happened, in the last 5 years, the SKA, there's been about $470 million invested in Western Australia. So this is a good deal. It's not just an interesting scientific experiment, this is actually a good deal for Western Australia. The federal government has built supercomputer centres, it's built fibre optic networks that connects the site down to Perth, it's built power stations, it's built ICRA, it's built the telescopes. So there's a lot of money flowing into Western Australia because this is such an exciting experiment, but it's also something governments find exciting as well. They find it exciting for the opportunities that it's going to develop. So what's next for the SKA? 2013 through 16, we're going through this design phase, and we actually design the telescope in great detail. 2017 through 2022, we're actually going to construct the very first phase of the telescope. It's about 650 million euros worth of construction. The whole project is about 2.5 billion euros worth of construction. Most of that money will flow into South Africa and Australia as part of the construction project. And then, of course, 2022 to 2026, we'll basically build the rest of the telescope and start doing science. So this is a great opportunity for Western Australia, as I said, because we've already created a supercomputer centre, created fibre optic networks, created a new scientific institute, created new telescopes. Lots and lots more benefits will be flying to the state as time goes by. In particular, in terms of information technology and data technology. The SKA is not only a revolutionary scientific instrument, it's the world's biggest producer of data. So the SKA will generate more data in a single day than the entire planet generates in 1 year. Okay, so one object, the SKA, more data in a day than ever it produces in a year. The data traffic inside the telescope will exceed the traffic in the entire internet in 2025. Not today, in 2025. The world's largest computer system will be in Perth. The world's largest database will be in Perth. So you can imagine if you've got that kind of opportunity here, you will start generating interest from ICT companies, from large companies who also are interested in data, such as the mining industry. So there's lots of synergies here that we can play off each other because there are these amazing opportunities for the technology of the SKA as well as the science of the SKA. One of the other most, to me in some sense, one of the most amazing opportunities is the educational one. So this is an inspirational project. This is a truly transformational project. And people love astronomy, and you guys are here tonight because you love astronomy. And then, you know, the person in the street loves astronomy. Astronomers are very lucky. We have these beautiful pictures and things we can show people and excite them about the universe. And that's not true of necessarily mathematics or biochemistry or whatever it happens to be. You know, we've got beautiful pictures to sell. So we're very lucky about selling our subject. And we have Planetarium that do a great job in that sort of thing as well. So education and excitement and careers and motivation is very much something the SKA will do. Speaking of motivation, this gentleman here was very motivational for me, and we unfortunately lost him a few years ago. I was a child of the 1960s. I was in high school in year 10 when the man landed on the moon. That was transformational for me. It changed my life because, and lots of my colleagues, because we all became scientists and engineers. And I think we can attribute a lot of it to the Apollo program. I think the Apollo program of the 1960s transformed the world, transformed kids in the world, so it transformed me, because it was so motivational, so exciting in some sense. I don't think much has happened, to be honest with you, at the same level since then. I don't think the world has been through this kind of excitement since the 1960s. I think the SKA is the modern example of Apollo. I think it is the transformational, motivational, scientific experiment which will excite kids to do science and technology, will excite industries into new discoveries, will excite all of us because it's astronomy, but also will find the missing clues, the missing pieces of that puzzle that will help us join our ideas of the universe together. So, West Australia on the threshold. Lo and behold, all this excitement is happening right here in Western Australia, on our doorstep. And that's even more amazing to me. The fact that, you know, I've been all over the world all my career. I've done telescopes in Chile, I've done telescopes in America, I've done telescopes in Europe. To come home to Australia, to have a chance to do this in Australia, has been truly revolutionary. And the fact that it's here in Western Australia means a lot to this state, a lot to the city, and I hope a lot to you. So I hope you enjoyed it. Thank you. How do we take any questions?
How long before the first data and information comes from this project? It's coming already, I guess.
It's coming already. Those pathfinders, those little precursor guys, the spider one, they've had about 2,000 or so of those little spiders out there since this time last year. And so it's already generating data, and that data is flowing from the site down the fibre optic to here, to the Pawsey Centre, and then off to the various places around the world. And that's just a 1% little experiment. And it's already basically filled up the Pawsey Centre, right? So, you know, the ability of these things to produce data is rather amazing. So yeah, so we're in kindergarten with this kind of data volume. Yep.
A question about the Big Bang, if I can.
Yeah, sure.
Over the years, we've heard how the estimate of the starting point started off like as big as a beach ball, and then it's got shrunk down to the size of a basketball. And I think Brian Cox the other day was talking about the starting point is the size of an atom. And how do we reconcile that with the density that we perceive in black holes that we know are at the centre of the galaxy?
Sure. So this is
hundreds of billions of these, and if you compacted them, you would have a size of a certain amount. Is it they're trying to, outdo each other in terms of extremity?
A little bit.
How small?
So it goes back to the sort of the basic point I was trying to make earlier on, that when we try to think about the Big Bang, and in principle it can be down to the sizes of atoms, everything starts to break, okay? Because it turns out you need an infinite force to change it. You need infinite time to change it. You need an infinite amount of energy to change it. It doesn't work because we know we're here. Something happened. So it's clear we've got something wrong. Something's wrong with our thinking about this early, very, very early stage of the universe. Maybe it's something really simple, like, well, the universe never actually started from something which was as small as that, and maybe it was bigger than that for some reason or other. Or maybe the universe, goes through these sort of bounces and things. It doesn't actually get to that small size ever. So there's a number of competing ideas, and all of those ideas have predictions, and those predictions can only be tested by doing something like SKA experiments. So we're on the way to find out, but at the moment we're all confused. Yep.
Up to now, and this is very simplistic, I know, but astronomers have spent their time gazing into the sky with a telescope and spotting something, finding something, naming something,
Yep.
and analysing what they see.
Yep.
What's going to happen is that we're going to have so much data
Yep.
that no one person can look at all of the data all the time.
Correct.
Astronomy will change into
Yep.
gazing not at the sky, but gazing at bits of data and trying to find something different or a pattern or something
Yep.
that tells you something. Am I right? Or
You
what
are
gonna look at?
you are describing astronomy as it was. Yeah.
Of bits of information
You're
coming
just,
at you
yeah.
every single second.
Sure. You're describing what astronomy was like probably 20, 30 years ago.
Sure.
So 20, 30 years ago, we had lots of data getting spewed out of telescopes, and people spent a lot of their time processing the data and picking out objects that were interesting from on a computer screen and doing it that way. We can't do that anymore, not even that anymore, because the amount of data that the SKA generates, you can spend your entire life generating screens of pictures with. So to really get the information from the SKA, we have to teach machines to be astronomers. Okay? We actually have to teach these computer systems to be able to make decisions about the data they're taking. Now, that's possible. And in fact, it's an interesting possibility because everybody else in the world wants to do the same thing. Google want to figure out, what sort of milk you buy by figuring out, when you went to the supermarket, what was on the shelf. And, figuring out stuff from data is what everybody's doing right now. And astronomy is probably the most challenging figuring out stuff from data problem. That's why other companies are interested in what we're doing. But it is, we have to get the machines to make some of the things happen. In other words, boil down this enormous bucket of data into a size where me as a human being can actually do something with it.
But that means you're building, let's say, for example, to use an analogy, like an electrocardiograph that is looking at this data, looking for patterns or looking for something. But in order to build that machine that's going to do the analysing, you almost need to know what you expect to find.
Very good.
Maybe what you're going to find isn't anything like what you think.
Good. So two very good question. Two parts of the answer. Number one part is we're doing these simulations, right? So the simulations are kind of guiding our eye about what we might expect to see, right? Number one. So we're not completely in the dark. The simulations, the physics is helping us guess in some sense what we might see. But you're correct. It is entirely possible that we'll find something we didn't expect. And in fact, that's almost the most exciting thing, right? So if you look at, and this is the track record of telescopes. If you look at all the telescopes that were on that plot before, and you ask, what are they now famous for? Almost all of them are famous for something that they weren't designed to do. So astronomers are very much aware of your problem that you pointed out, and I think it's a very valid problem. So we have to be able to find the unknowns, the unknown unknowns even.
There's a question over here.
Yep. Yes, sir.
Can you tell us how you will handle the problem of a research PhD who gets his PhD in a finite length of time, anywhere in the procedure here? So let's go to the fully operational thing. Before he gets to 80 years old or something.
Yep. Look,
It's going to redefine the whole concept.
I think for quite some time, and you know very well, that space projects take 20 years to 30 years to run, right? So people can spend their entire careers doing one project. The SKA is a bit the same, that people are involved now with the design, where people in the future are involved with the construction, people after that are involved with taking the data, etc. So it'll be an evolution, but I do think, PhDs will probably still stay 3 or 5 years. I mean, if the SKA is operational, when the SKA is operational, one of these surveys, one of these new map building exercises can be done in about 1,000 hours of observation time. Okay, so we're not talking 20 years of observation time, we're talking about 1,000. It's because it's a square kilometre, it can actually collect the data in a relatively short amount of time. So it's still talking about human timescales for amassing data, human timescales for PhDs, but the evolution of the project is beyond PhD scale. So PhDs will slot themselves into various parts of the project along the way, but they're not going to extend to 20 years.
But the nature of creating the experiment is going to change, surely.
I think what will change is we'll go down the same path as particle physics. We'll go down the path of very, very, very large teams. So individual astronomers, going to a telescope and sticking their eye to the back of it, I think that model is gone. What you'll find is you'll have very large teams of astronomers from all around the world getting together, applying collectively for time in the telescope, having data distributed through the internet to their home supercomputers. And so the model of doing astronomy will change, I agree with you.
Will be doing anything to confirm inflation? I know they had earlier this year or last year, they were talking about that confirmed inflation, but there's been some talk that maybe that was to do with dust closer to.
Yeah, so exactly. The inflation is it's part of this story. Okay, so another part of the cosmic story is that at some point in the history of the universe, not only did the universe expand, but it expanded extremely rapidly. So there was an early phase of extremely rapid expansion, then a next phase of sort of slightly slower expansion. That really rapid expansion is called inflation, and people want it for various reasons because it solves certain problems. We don't know, we have some ideas what might have caused it, and recently people thought they found evidence for it, but they didn't. Because there was some problems. But inflation is one of the ingredients of what we call a standard cosmological model. We have a standard model of cosmology. Inflation is part of that story. We think it's important to the story because it solves some problems. We still haven't found its source. Just like we haven't found the source of the dark energy, we haven't found the source of the inflation either. Yep.
So when the Big Bang happened, all the diagrams you seem to go one direction.
Yep.
Shouldn't it be in the center that it went everywhere?
It's just a cartoon. Okay, so yes, indeed, I could draw a circular rather than an hourglass. I could draw a circular thing, no problem. But it's just a diagrammatic way of showing progression of time and distance.
So everything is moving away from the center point.
Correct. Yes. Yep.
I just want to understand something. What we're seeing is that other galaxies are all moving away from us.
Yes.
Do we know if that's true at every point in the universe?
It's not absolutely true everywhere in the universe. The reason is quite simple. That if you, this is the Milky Way, and there are galaxies which live near the Milky Way exerts a gravitational force on them, right? So they could have started moving away from each other in the universe, but eventually, if gravity is strong enough, or if they're close enough, then they stop. They start slowing down and start even actually approaching one another again. Right? So in the small scales, the scale between individual galaxies, for example, galaxies can be moving in orbits around each other, so it's not true that everything's expanding. It's only when you get to the scale of hundreds and thousands of millions of galaxies that the universe is still expanding nice and uniformly. So yes, good question.
Thank you.
A lot of our understanding has come from the precision and imagery that we've got from the Hubble telescope.
Yep.
And about 2018, they're talking about this new James Webb telescope. Is there going to be some interaction between
Yes.
SKA and the James Webb? And
Yep.
how would that work?
Exactly, very much so. So James Webb Space Telescope is a successor to Hubble. It's much bigger. Hubble was about 2 meters. JWST is about 6 meters across. And it will actually get back very close to the first objects, right? So it'll give us, if you like, a view in the optical part of the spectrum, and the SKA will give us the view in the radio part of the spectrum. In fact, the radio waves can go back further than the optical because the radio can see the gas before the stuff is even formed, right? So they have to work together. The story will be the universe was hot and expanding, it got cooler and cooler, and then when it's really cool gas, the radio telescopes can actually see the cool gas, and then things started to condense out, start glowing, and then JWST will start seeing the glowing things. So that transition from no glowing things to glowing things needs the SKA and JWST to work together.
We'll make that the last question.
Just one on the technology. I
Sure.
mean, given that it's 10 years before it's fully functional or
Yeah,
whatever,
yeah.
the equipment being put in place now and being used now, is that going to be superseded in 5 years?
Some of it, yes. I mean, the stuff which has been put in place now is really just test equipment. It's really just verification equipment. It's not the SKA. The SKA hardware will start going on the site probably about 2018 or 19. Okay. So that's, we're still in the design phase, and we're doing the design based upon the experience we're getting with the stuff we've got there right now. But we might reuse the trenches and some of the cabling, but all the other stuff will not change. Okay.
Okay, I guess it's time for me to bring proceedings to a close and to offer some thanks. And first and foremost to Peter Quinn for what was, I think, an astronomical tour de force. Can we please show our appreciation?